In this example, we're asked to find the specific internal energy of compressed liquid water at a pressure of 3 megapascals. We'll assume that's an absolute pressure, and a temperature of 60 degrees C. So in this example, I'll just refer to the solution since I'm going to need to refer to a table and do that rather than using a blank piece of paper. So I've shown here a table for the properties of compressed liquid water. This comes out of the Moran et al. Book, the 7th edition, table A5. And we're asked to find the specific internal energy at a pressure of 3 megapascals and 60 degrees C. So if you look at that table, the table itself is divided into subtables. So for example, here you see a subtable corresponding to 25 bar or 2.5 megapascals. And then this one is 50 bar, 5.0 megapascals. You'll notice that there is no table, no subtable for 3 megapascals. Remember, we need to find this for 3 megapascals and 60 degrees C. So we don't have one for 3 megapascals, right? So we don't have that one. And we also, if you look over here, you don't see one for 60 degrees C either, right? So what we're going to have to do is do a double interpolation, double linear interpolation, since we don't have the right pressure and we don't have the right temperature. So the correct specific internal energy will be somewhere between these 4 values. Let me highlight it. So here's the one set of values. This is the specific internal energy at 2.5 megapascals and 40 degrees C and 80 degrees C. And then the other set of values it'll be between will be these. So this is the specific internal energy at 5 megapascals and 40 degrees C and 80 degrees C. So somewhere in this range we'll have our specific internal energy for the 3 megapascals and 60 degrees C. So how do we figure out, how to find this? It's somewhere in this range. So as I mentioned, we'll have to do double linear interpolation. And the way we do this is given up here. So the first thing that we'll do is we'll interpolate with respect to temperature. Now you can do this so we'll do with respect to temperature first, and then we'll do with respect to pressure after that. But one could do this in either order. It's going to be the same regardless. So we'll interpolate first with respect to temperature. So what we're going to do is we're going to interpolate this table first to find out what the specific internal energy is at 60 degrees C. All right, so the way we do that is we use linear interpolation on this table. Linear interpolation is basically just using the equation of a line that looks like this. In this case, our y values will be the specific internal energy. So specific internal energy at 60 degrees C minus the specific internal energy at the lower value, which would be 40 degrees C. You can see that right here. This is our lower value. This is our slope. The slope is going to be dependent on our values at 80 and 40 degrees C. So we're going to use the specific internal energies at 80 degrees C and 40 degrees C divided by the change in temperature at 80 degrees C and 40 degrees C. So we're just getting how these values change with respect to temperature. So that's our slope. So this corresponds to that. And then our x's here will be just the temperature variation. So it'll be like the temperature at 60 degrees C minus the temperature at our lower bound, which is the 40 degrees C. So we're just using the equation of a line with these 2 points that straddle the 60 degree value to determine what the specific internal energy will be between those two. So that's how we end up with this equation. Specific internal energy at 40 degrees C, specific internal energy at 60. There's our slope, just how the specific internal energy changes with temperature. And this is the temperature at 60 degrees, temperature at 40 degrees. So we can do that calculation, and that's given down here. So here are the specific internal energy values at 40 and 80. They're just these values right there. Here's our temperatures at 40, 60, 80. Those are just 40, 60, 80, pretty straightforward. So when you work out the linear interpolation for that left-hand table, you get this value. You see it's 250.77, which is somewhere in between those two, which makes sense. Now you can do the same idea over in this table where the pressure is 5 megapascals. So that calculation is given right here. It's the same exact idea, but now we're just basing it at 5 megapascals. You can see that right there. And when you do that calculation, you get this value right here. So that comes out to be 250.34, so a value somewhere in between here. So that gives you the specific internal energy now at 60 degrees C for the pressure of 2.5 megapascals and then 5 megapascals. So then to get the specific internal energy at a pressure of the 3 megapascals, we do another linear interpolation between these two values. Right, so that one is given here. So this is showing how the linear interpolation based on pressure. So you can see our pressure is now our x variable. Right? And we're going, when we do that linear interpolation, the lower bound is the 2.5 megapascals. That's right here. And then we're trying to find it at 3 megapascals. And then the slope is based on the difference between the value at 5 megapascals and 2.5 megapascals, because here's our 5 and here's our 2.5. Okay, so hopefully that all makes sense. We're doing two linear interpolations based on temperature, one for this table, one for that table, and then one linear interpolation between the pressures. And when you go through all that, we'll get that this should be a little u, the specific internal energy at 3 megapascals and 60 degrees C comes out to be 250.68. So it should be a value somewhere between these two, which indeed it is. And as I mentioned before, we'd get the same result if we did a linear interpolation first according to pressure. The way we could do that would be we would find the specific internal energy at 40 degrees C at 3 megapascals. So we'd linear interpolate between those two values, and then do a linear interpolation based on pressure at 80 degrees C. So that would be between those two values. And then once you have those values, then do the linear interpolation between the based on the temperature, and then that would give you the value at our desired 60 degrees C and the 3 megapascals. Okay, so hopefully all that makes sense. It's just using linear interpolation a few different times. It's a little more tedious than doing it just once, but if you have a temperature and pressure that don't fall into nice values within the table, you have to do the linear interpolation a few times. So we'll end it there.